Let's talk a little bit about how we can describe position, velocity, and acceleration for an object in simple harmonic motion. So first of all, simple harmonic motion is the study of oscillations. This is any cyclical motion like a vibrating violin string, a spring that's oscillating, or a swinging pendulum. We will usually be looking at a spring. It's just the easiest one to visualize. So if I take this mass and I bring it upward and I release it, we see that its position as time goes on follows this shape. Now this is a cosine graph, which is not that important if you're not in trig, but it can be helpful if you are. So we see that as time goes on, it changes speed, moving slowest at the top and bottom of its swing, and moving fastest as it passes equilibrium. Okay, so going back here, in order for us to have simple harmonic motion, we need a force that's always trying to get the object to return to equilibrium. So for a spring is always acting in the direction towards the equilibrium position where the spring is at its rest length. When the spring is at equilibrium, the force there is 0. However, since it's moving when it gets there, it continues to move past it. We can make sense of simple harmonic motion by comparing it to circular motion. And so for that, we're going to actually go back to this for a moment. If I look at simple harmonic motion and compare it to circular motion, I can see that as an object goes around a circular path, its distance from the center is always constant. However, the y component or x component, depending on your prerogative, is always changing. And so if we compare in this setup with a vertical spring, the y component of the simple harmonic motion to the y component of the circular motion, we can see that they're the same. To get a value for the component of the position as it goes around the circle, we can use the equation x equals r cos theta, where we can visualize just the x component of the position vector of the object in uniform circular motion as it goes around. So we can use this expression to determine the position of an object that's in simple harmonic motion. The only problem is if we're looking at an object that's oscillating back and forth, it's not obvious what this meaning of theta is since it's not traveling around a circular path. So we're going to take this equation and we're going to make it a little more specific for simple harmonic motion. First of all, instead of traveling in a circle with a radius, it's traveling back and forth with an amplitude. Amplitude is the greatest distance it ever reaches from equilibrium, and we use a capital A to represent amplitude. Also, instead of talking about an angle theta, we can take advantage of the fact that angular displacement equals angular velocity times time. And so we can use this expression, omega times t, in place of theta to discuss how far through its cycle the oscillating object is. So this letter omega now doesn't mean the same thing it does for circular motion, because in circular motion omega is a velocity. It's telling you how quickly, not only how quickly it's spinning, but in what direction. For uniform circular motion, omega is a vector. For simple harmonic motion, omega is a scalar. Instead of being an angular velocity, it's an angular frequency. It's not very different. The calculations will be done the same way as angular velocity, 2 pi over the period. The only real difference is if angular frequency is always positive, it's not a vector, it's a scalar. And one way to think of why that is it's basically the shadow of the object in uniform circular motion, and so you can't tell then from the shadow whether it's traveling clockwise or counterclockwise. Okay, so the graph that we saw the spring trace out on the simulation is a position versus time graph. And so when we're building a position versus time graph, we need to be able to establish a couple things. First of all, we'll have position on the x and position on the y, time on the x. The amplitude is the farthest the object ever gets from equilibrium as it's oscillating. We call that the amplitude. As we mentioned on the previous slide, the position function is x equals a cos omega t, where we can calculate omega. T, the period, is the time for one full cycle. That's the time to get from the amplitude back to the amplitude again, or from any position to back to that position again, going in the same direction. And so if each of these hash marks is 1 second, in this specific graph, the period would be 1, 2, 3, 4, 5 seconds. That's the time to get back to where it started. Just like in every other context, frequency and period are inverses, so if the period is 5 seconds, then the frequency would be 1/5 of a second. It's just the number of cycles per second. And here, if we wanted to plug in and calculate omega, it'd be 2 pi over 5. Okay, so now we're going to talk about the velocity. So going back to this, I'm going to go back to the velocity, turn this off, turn this off. Oops. Okay, so the velocity versus time graph doesn't say where it is, it says how fast it's going. So if I bring this to the top and release it here, its initial velocity is 0, and then it's going to head in the negative direction. I thought I was going to get a graph. Oh, sorry. Now I get it. Okay. Okay, trying that again. Starting at 0 velocity and then heading in the negative direction. Here we go. So this graph is showing how fast it's going, not where it is. It stops at the extremes, and it's going fastest as it passes equilibrium. This could be a little bit tricky to visualize, but hopefully it at least makes sense that when it gets to the top and bottom, that's when it stops, and when it passes equilibrium, that's when it's moving the fastest. A velocity versus time graph in simple harmonic motion is going to be a negative sign graph. Doesn't matter if that's not something that you're familiar with. Basically just starts at 0, goes in the negative direction. Starting at 0, that's the case because we assume that we're starting the simple harmonic oscillator at a positive max position. The equation for velocity, v equals negative v max sine omega t, v max being the maximum speed, which happens when it passes equilibrium, omega, same as before, 2 pi over t. We will not use this equation very often. Honestly, most of the time if we're trying to figure out velocity and position, we'll be using conservation of energy. One helpful equation that can be a shortcut is that v max, or the maximum speed, is going to be equal to omega times the amplitude or the maximum position. And then finally, we're going to talk about acceleration. So the acceleration graph and the position graph are related because the farther you are from equilibrium, the greater the force is, and the greater the force is, the greater the acceleration. So actually, let me start by just showing you the acceleration graph. So we see that the acceleration of the block and its displacement are always in opposite directions. When it's above equilibrium, it's accelerating in the negative direction. When it's below equilibrium, it's accelerating in the positive direction. If I do turn on the displacement versus time graph, we can see that they're basically mirror images of each other, although they definitely can have different amplitudes. It just depends. But they have zeros at the same times, and they have maxima at the same times, but they're just opposite. So for an acceleration versus time graph, it's easiest to think about how the force exerted on the object is related to how far it is from equilibrium. When it's at a maximum position, acceleration's at a max because the more you stretch a spring, the more it wants to go back to equilibrium. The one funny thing is that it's always opposite the displacement. So if you pull something to the right, the acceleration will be towards the left. That's this negative sign here. Otherwise, the form of this equation is very similar to the position function. If we don't know a max, we're usually going to go back to Newton's second law or Hooke's law, F equals negative kx. A shortcut that only works to find the max acceleration is A max equals omega squared A. So that was a crash course on position, velocity, and acceleration in simple harmonic motion.